Hello everyone. Welcome to the latest episode of the Ask Abhijit show. I hope you're all doing very well. As you know, today we are discussing science, and that's what we will discuss. So let me first take a look at who all is there and greet you all. So I can see Anshuman, Yuvraj, Jatin, Harshvardhan, Shweta, Prachit, Dragon Master, Abhishek Sharma, Swapnil, Chirag, Parth, Akshay, Suraj, Darshan, Vault Gaming, Bulldozer Baba, Alpha, Deepak, Crazy Brain, Umbrella Corporation, Priyanshi, Samarth, Pratham, Dar, Jatin, Rajat, and lots of other people. Good evening, good day to all of you. And with that said, I will get right into the questions. As always, a lot of questions. So let's see what we have for today. What are today's questions? Let's go with question number one. Question number one is by Tejas. Tejas says, why is 0 not equal to 1? Please answer it in a way that viewers like me won't fall asleep. I could offer you a mathematical proof that 0 is not equal to 1, but how do I prove it in a way that you won't fall asleep? So how many of me do you see right now? How many Abhijits do you see right now? You see one Abhijit, right? And how many Abhijits do you see now? How many? This is 0. You can see 0 Abhijits now. Now it's 1. Now it's 0. Magic. So that, I hope, proves that 0 is not equal to 1. There you have it. That is your non-mathematical but physical proof that 0 is not equal to 1. Hope that makes sense, and I hope that it did not make you fall asleep. Okay, next question. What's the next question? The next question is by Swapnil. How was a pig heart transplant in a human made possible recently, and why did it fail so soon? Right. So people have been testing out various ways of implanting organs from other species into humans in order to overcome the human organ shortage. So many people have organs that fail in old age or because of whatever reason, hearts and lungs and kidneys and livers and other organs. Yes. So there is there's a high demand for organs. And of course, the only way to acquire organs is from somebody who unfortunately passes away and the organs are still intact. Yeah. Or somebody who's brain dead and whose family decides to donate the organs for somebody else's benefit. That sort of thing. But such people are very scarce. Typically, when a person unfortunately passes away, the body decomposes very fast. Unless you're in a medical environment where the organs can quickly be harvested and saved, the organs will go to waste. That's how it is, unfortunately. So, a better alternative, if it is possible, is to find a way of transplanting non-human organs into humans. But that obviously has lots of problems, right? Because first of all, the main problem in organ transplants is rejection. Our immune systems know what is our own tissue and what is tissue that doesn't belong to us. They understand that. Our immune system understands that. Even if you get a transplant from another human being, your immune system will immediately know that this is not your tissue, it's from somebody else, and it's going to attack that. It's going to regard that as a foreign invasive force. It's going to go ahead and try to destroy it, and the immune system is very good at doing this. It typically destroys organs very rapidly that are transplanted from another person into you, or into a donor, into a recipient, from a donor to a recipient. So this is called organ rejection. It happens very rapidly, and to overcome this problem, typically you give immunosuppressant drugs to the recipient, which suppresses the immune system, which has all kinds of other problems. So it's a tightrope act that you have to do. You should not suppress the immune system so much that the person will fall prey to any kind of illness and die from that. But also the immune system should not destroy the organ that the recipient needs in order to stay alive. So typically you give certain drugs that suppress the immune system to a certain extent, but keep the person reasonably healthy, right? It's usually a cocktail of immunosuppressive drugs and all that. So that's when you have a human to human transplant. There's this new process called xenotransplantation. So it's from one species to another species. Now typically pig organs are quite similar to human organs, and that's why the people have been exploring the possibility. Scientists and doctors have been exploring the possibility of transplanting porcine organs into humans, xenotransplantation. So initially they did tests on baboons. Baboons are a species of monkey. They're not apes, they are monkeys, right? Yeah. So scientists tested transplantation of organs from pigs into baboons. It worked reasonably well. Then what they did was they tested the connection of pig organs, like kidneys, essentially, I believe, to brain dead human beings. So people whose brains have stopped functioning, they're dead. They're in the vegetative state. They have no chance of recovery. So that sort of thing was tested out, and it seemed to work well. The kidneys of pigs were attached to these human bodies that were no longer viable. They were brain dead, and the kidneys, I believe, functioned reasonably well. They functioned well as per expectations. They produced urine and all that, so that worked. Now, in January 2022, this year, there was this elderly person in the US who had a heart that was failing. That person was guaranteed to die. He had no way out, and he was not eligible for whatever reason for a human transplant. So the authorities gave the go ahead for a xenotransplantation procedure. A pig heart would be implanted in that person. Uh, and this was not any regular pig. It was there's this company, I don't know what's the name of the company, you can look it up, which engineers pigs that whose genes have been edited. So what is done is that the genome of these pigs is edited in such a way that you implant some human genes in there, and you remove some pig genes. So that kind of tricks the human body, which will receive the pig organ, into believing that this could possibly be a human organ. So it's like stealth mode. You activate stealth mode and you implant the organ in the recipient. So that sort of procedure was done. They raised these pigs that have these mixed genetics, whose genes were edited, and then obviously one of these pigs would have to be sacrificed, and you remove the heart. That's how it's done. It's sad, but that's how it is. You remove the heart, and so one of these pig hearts was implanted in this person in the US, I believe in January this year, 2021, and it went well. Yeah, the person woke up from the operation. The heart was beating as well as could be expected, and the person survived two months, I believe, before he passed away. And everything was going well, but then suddenly the person started falling ill. He was not well, and what they discovered is that it was not that the organ was rejected. They had given a cocktail of immunosuppressive drugs, I think on two occasions, to this person after the transplant was done, and his immune system was not attacking the pig organ, the pig heart. It was not rejecting it. What happened is that there was some virus, some pig virus, that was present in this organ, in the tissue, in the heart tissue. I think it was called the porcine cytomegalovirus or something like that, though I may have got it wrong. That's what this virus was called. Now, they had engineered the pigs and they had given the guarantee, this company, that there would be no viruses, but clearly they messed up. So this organ, this heart, had that virus, the porcine cytomegalovirus. Now, this virus is not something that typically infects human cells. It infects pig tissue. Now, inside a pig, these viruses are prevalent, and the pig's immune system ensures that the viruses are suppressed and they don't create any trouble. But when you remove the organ from a pig's body, you implant it into a human body. The human body has a human immune system, not a pig porcine immune system, and that's why the viruses start proliferating. That's what seems to have happened. So when they finally did the autopsy of the organ and all that, they found that there was an unbelievably high amount of virus in there, and that's possibly what had caused the degradation of the organ. It stopped functioning as it should have. The walls became thickened and more stiffer than what you would expect, and something like that, right? You can look up exactly what it was. There's plenty of articles about that. And so that's what happened. So there's a couple of reasons why this could have happened. First of all, the company messed up. The company that produced these pigs had given a guarantee that there would be no viruses, but yet they messed up, and this virus was present in the tissue. And secondly, the immunosuppressive drugs the doctors had given to the person, intravenous immunoglobulin or whatever, it contained antibodies that acted against pig cells. So not only was there the problem of the virus, but the antibodies that were given to the patient, acted against the pig cells and would have possibly damaged the heart tissue in some way. So there are a number of reasons why eventually the heart failed and the person passed away. But it's not because of organ rejection, which is good news. Which is good news. First of all, this person was as good as dead. He essentially had no hope of survival, so he got another extra 2 months of life. Eventually, the heart failed, but it was not because of organ rejection, which is a significant step forward. So if these problems that arose could be circumvented, firstly by ensuring the next heart has no such viruses, and secondly, you don't give antibodies that act against pig cells, then possibly the next such recipient would have a much longer life, and the heart would last much longer. So it's that's the latest news. Human organ transplants have been happening for a very long time. I believe right now the heart transplant from one human to another, from a donor to recipient, is a reasonably routine uh, reasonably routine procedure. It still has risks and all, but once the heart is implanted, I believe the median life expectancy of a recipient is about 15 years, which is excellent, which is an excellent outcome. So that's where we are today. But in the future, I believe xenotransplantation will be researched upon much further. In the future, you may have such procedures becoming more commonplace, and that would essentially, if that can be perfected, and if you could achieve the same kind of outcome, 15 years median lifespan, life expectancy after transplantation, that would be a massive step forward. That would be a massive step forward, and the problem that we face today is this organ shortage. There are so few organs available and so many people who need that. So that could solve that problem. So that's where we are. It's a very interesting step forward. Obviously, it involves sacrificing the lives of pigs, but well, that's unfortunately where it is. That's how it is. So that is the news. That's what happened. That was the story of the pig transplant that happened this year. Pig heart transplant. It failed, but it did not fail because of organ rejection. It failed because of other reasons, like I just outlined. So that's the story. Okay, Vashist says, as per the abiogenic petroleum origin theory, most of the Earth's petroleum and natural gas deposits may have been formed inorganically, like the methane and other hydrocarbon fuel deposits on Titan. Thus, the dinosaurs may not be the origin of our fossil fuels. How far is this true? Okay, so the mainstream theory, the widely accepted theory, is that the origin of petroleum is from the decomposition of organic matter, of plant, etc. matter. The abiogenic origin theory says that it could have originated from non-living materials. For instance, it is well known that various asteroids and comets contain lots of organic compounds, right? Complex hydrocarbons, even amino acids, which amino acids are the basis of life, right? Or are the basis of proteins. So because of that evidence, it is speculated that maybe the petroleum and natural gas and fossil fuels on the Earth could possibly have had an inorganic or abiogenic origin. This theory is not a mainstream theory. It is not very well accepted. If you look at the various mechanisms through which petroleum and fossil fuels could form, the biogenic theory makes a lot more sense. We know that life has been present on this planet for billions of years. Initially, it was unicellular, then multicellular life, very simple life. Algae, you had algae all over the planet in the oceans, yeah. And so the theory is that when these algae die, algae are typically unicellular plants, right? So typically when these organisms die, they would sink they would decompose. But in certain conditions, when you have stagnant water that does not have mixed oxygen dissolved in it, and when these algae die in stagnant water, they go to the bottom of the pool of water, maybe the bottom of the ocean, where you have such conditions. And there are anoxic conditions, which means there is no oxygen available there, which means decomposition cannot happen. Then you could have a massive amount of this organic material that sinks to the bottom of the ocean. Eventually it goes underground. You have heat under the surface of under the surface of the earth, in the earth's crust, because of a number of factors. This heat catalyzes the production of what eventually becomes petroleum. And depending on the depth below the earth's surface, you could either have liquid petroleum, you could have kerogen, I believe, which is one stage prior to the formation of petroleum, uh, or oil, crude oil. And if it is below a certain depth, then because of a process called, I believe, cracking, you would have the formation of natural gas. So that this theory makes a lot more sense, given that there was this vast proliferation of life on the earth, which is known from a large amount of evidence. Yeah. So that theory makes a lot more sense. We know that Titan has hydrocarbons uh, all over its surface in the atmosphere, uh, and we know that hydrocarbons and even amino acids are found on asteroids and planets. And yet on Earth, the biogenic theory makes a lot more sense. And now you're talking about dinosaurs. Dinosaurs are not the origin of fossil fuels. It is these simple forms of life from the very early phases of our planet's existence that are the origin, that are the source of the origin of our fossil fuels, whether it is crude oil or gas, you know, natural gas. So that is where we are. That is the answer. The abiogenic petroleum origin theory does not make a lot of sense. The theory that makes way more sense is the biogenic origin theory of petroleum and natural gas. Okay. Ira says, most unanswered question to me is that why are oceans deep inside cooled with high pressure, but as we go deeper inland under the surface of the earth, it becomes hot? What is the reason behind this? Could you please answer this and explain it as well? Isn't this a very interesting question, fascinating question? You go below the ocean surface, the oceans get colder and colder. Yeah. But when you drill below the surface of the earth, in the crust of the earth, the deeper you go, the hotter it becomes. I mean, for instance, you go about 500 kilometers below the surface of the earth, the temperature is almost 2000 degrees Celsius. Almost. Yeah. You go 3000 kilometers below the earth's surface, the temperature is around 3000 degrees Celsius. And the inner core of the earth, which is between 5 and 6000 kilometers in depth, is believed to have a temperature of about 7000 degrees Celsius, or Kelvin Celsius, almost the same, right? So that's how it is. As you go deeper under the earth's surface, the temperature rises, and yet under the oceans, you go deeper, the temperature gets colder. Why is it so? So to understand why it is so, we have to understand what causes the heat. What is the source of the heat under the earth's surface? So firstly, the oldest source of heat under the earth's surface is planetary accretion. So our solar system formed from a protoplanetary, protosolar, protostellar disk, yeah, which gave birth to the sun and the other planets which are in existence around the sun. So that is number one. So that is the source of that is the first source of heat. Am I visible, or is there any problem in the connection? Is my image clear, or is it blurred? That's the question. I get the feeling there may be some problem. Maybe not. Maybe it's fine. Is my image visible properly? Am I visible? It looks like I am visible. All right. There may have been a brief network issue. It seems to be good now. All right. All right. Thank you for letting me know. Okay. So the question is why are the oceans cold as we go deep inside, and why is the surface why is the earth why does the earth get hotter as we drill deep inside? So the first source of heat is residual heat from planetary accretion. The Earth formed from very hot material, the protostellar disk, and there is a lot of heat left behind from that as you go deeper into the Earth's surface. Below the Earth's surface, below the you have several layers of the Earth's surface. You have the crust, then you have the mantle, then you have the magma layer, then you have the outer core and the inner core. And as you go deeper, it's hotter because at the in the interior of the Earth, you still have this heat left over from the formation of the solar system and of the Earth. So that's number one. The second source of heat in the surface of the in the interiors of the Earth is radioactive decay of radioactive isotopes, nuclides, such as uranium 238, uranium 235, thorium 232, potassium 40, and so on and so forth. There are a number of radioactive elements that decay. Radioactive decay occurs, and this radioactive decay gives off heat, and this contributes to the heat in the interiors of the planet. So that these are the two major reasons why the interior of the Earth gets hotter as you go deeper inside. Firstly, residual heat from planetary accretion. Secondly, radioactive decay of radioactive isotopes. Neither of these two sources of heat is present in the oceans, and that's why the oceans are much colder. And as you go deeper, see, heat rises to the top. Hotter fluids, if you have a fluid which has a temperature gradient, you will always find that the hotter part of the fluid rises to the top and the colder one sinks deeper to the bottom, whether it is air or whether it is of any liquid. So therefore, as you go deeper into the ocean, you will find colder and colder water. So that's why as you go deeper into the ocean, the water gets colder, but as you go deeper below the Earth's surface, the environment gets hotter. Very good question. I'm glad somebody asked this. Okay, next question is by Karan Sharma. There is an idea in string theory that the whole universe may be a hologram. The holographic principle suggests that what we all experience every day in 3 dimensions may really just be information on a surface located at the farthest reaches of our cosmos. What are your thoughts on this? Do you think we live in a hologram? If yes, are we just following a pre-written script? Okay, what is this holographic principle? What is that? Well, in a way, it's really hard to explain what the holographic principle is. I would have to explain what is conformal field theory, anti-de Sitter conformal field theory, duality, ADS, CFT, correspondence, all that. Let's not go into that. Let me give you an analogical, briefer, simpler, possibly, hopefully, simpler explanation. You've all heard of black holes. According to a black hole is a quantum object as well as an object that arises out of general relativity, right? So a black hole is an object that has an event horizon, a boundary of no return. You go beyond that, you will never ever come out. So stay out of it. All right, don't go anywhere near a black hole. Firstly, that is that. Secondly, a black hole has an event horizon, the point of no return, the boundary of no return. Inside, if you go inside the event horizon, if you cross the forbidden threshold, then inside the black hole you have empty space. That's what it is believed to be from the perspective of general relativity. You have empty space, more or less. But if you go inside a black hole, you keep going towards the center of the black hole, and as you reach the center, the strength, the force of gravity, the curvature of space-time becomes more and more extreme. And at the very center, you have what's known as this singularity. It's a monstrous thing, object, which is infinitesimally small. It's a point which has infinite curvature of space-time and infinite density. So as you go towards the center of the black hole, you get stretched out in the process called spaghettification. And at the center, you get squeezed out of existence, and you disappear. But your mass energy gets added to the mass energy of the black hole. That's what happens. Now, you as a physical human being are made up of particles and molecules and bonds and all that. That is a whole lot of information, quantum information, right? Let's, even if it's just a piece of if it's a human being or an atom or whatever goes inside, it has certain information that's encoded within it. When this atom or this human being gets sucked into the black hole and gets squeezed out of existence at the center in the singularity, the mass energy does get added to the mass energy of the black hole, but the information disappears. And that doesn't make any sense, because throughout the universe, from all our understanding of the laws of physics and of nature, information is never destroyed. And yet, apparently, inside a black hole, information gets destroyed. That is the black hole information paradox. And Stephen Hawking said that, so that's what he said. He did a lot of work on black holes from the general relativistic perspective, from a quantum perspective, also quantum field theory perspective, the semi-classical Hawking radiation you may have heard of, and so on. So Stephen Hawking said that when it comes to black holes, when something goes inside a black hole, the mass energy is added to the black hole, but the information is destroyed, which makes no sense. So the string theorists started working on it. Physicists who indulge in string theory, an interesting pastime. Just kidding. So string theorists started working on it from the 1960s, 70s, 80s, 90s. In the 90s, this new principle was put forth, and it was eventually called the holographic principle. It said that any object that crosses the event horizon leaves behind its information on the event horizon. This information, which is part of the object, becomes encoded, it becomes smeared out on the surface of the black hole, on the essentially on the event horizon, right? So the information is not destroyed. The object gets destroyed, its mass energy gets added to the black hole, but its information remains encoded, stays encoded on the surface, on the exterior boundary of the black hole, which is essentially a two-dimensional boundary, right? So that essentially says that the boundary of a black hole is like a hologram. It's a two-dimensional surface which shows you something that's three-dimensional inside. What's a hologram like? When you have a credit card, there is a holographic image on that, right? As a security measure. It's a flat two-dimensional image, but if you see it from different angles, it looks like it has something three-dimensional encoded inside. So a hologram is a two-dimensional surface that gives you information that has information that appears to be three-dimensional inside. So there are true holograms and false holograms. That I will not go into that. So if you extend this idea, the analogy of the black hole and information being encoded on the surface, to the entire universe, then our universe, if it is finite, it would have a boundary. And maybe all of the information within the universe, such as me, what's in me, what's in you, all of this, all the stars, planets, galaxies, everything, all of this information may well be encoded on the surface, on the external surface that surrounds our entire universe. So maybe our universe, if some great alien being were to see it from outside, it would appear like a hologram, a two-dimensional surface which encodes three-dimensional information within. So that is the holographic principle. That's the analogy I can offer you. I hope it makes sense. So our universe could very well be a hologram, and all the information within it could be possibly encoded in binary form or whatever form on a two-dimensional surface that envelopes it from the outside. So that is the holographic principle. It arises out of string theory, right? It was Gerard 't Hooft who came up with this initially. Then it was Leonard Susskind who worked on it, and other people as well. So that's what it is. Do we know if it's true or not? We don't know, but from the string theory perspective, it makes sense. That's the simplest explanation I can offer. Now, the last part of the question is, are we following a pre-written script? See, we all know the best theory of the origin of the universe is what is colloquially called the Big Bang theory. which says that all of the mass, energy, information, everything of the universe was once compressed into a single point, or something that was close enough to a single uh, zero dimensional point. The initial singularity that eventually, out of which space time expanded, and that is what we call the Big Bang. Now, if this is true, then everything that happens in the universe can be, if you reverse time, if you reverse the equations of time, we can go back to the origin of the universe. And again, if we take the time clock forward, then we can work everything back forward in time, which means that the entire universe, all the mechanics, dynamics, statics of all the objects, molecules, everything in the universe, atoms, subatomic particles, photons, everything follows differential equations. And these are very complex differential equations, but they are simply differential equations. So they will work forward in time and backward in time. If I mean, this is how it makes sense. That's the best theory that we have. And according to this theory, there are certain uncertainties, quantum uncertainties in the universe. The Heisenberg uncertainty principle says that the universe is uncertain. It's probabilistic. It is not entirely deterministic. And yet these are actual uncertainties. These cannot be factored into the equations. If you remove this randomness from the universe, then everything else follows the differential equations. All objects in the universe, subatomic particles, everything follows these differential equations. They are governed, their entire life cycle, the movement, everything is determined and governed by these differential equations, which means that free will doesn't exist. What I am saying right now was determined at the moment of the Big Bang. The very fact that I exist here was predetermined at the moment of the so-called Big Bang. And every single thing I speak and I do is predetermined per these differential equations that govern our existence, which means the thoughts that I have, the emotions that I have, everything is determined. So from that perspective, there is no free will, and everything is just the universe is made up of clockwork. There is this randomness, the quantum randomness, but that is, you can say it's an external kind of thing. It is not something that can be predicted. So beyond the fact that we have quantum randomness, everything else is predetermined. And the quantum randomness does not affect our will. So that's what it is. It's a very scary thought. I mean, obviously we understand next to nothing of the universe. Our best theories are actually quite crude and rudimentary and primitive. We understand less than 5% of the universe. So we should not get carried away and start saying that we know everything and there is no free will. But from the best theory that we have, which is a very poor theory actually, from that theory, it appears that it would appear like free will is an illusion and everything is like predetermined. But that may not quite be the case, because we only understand a very little tiny bit of the universe, and our understanding of the universe is far, far, far from complete or correct entirely. So that's what I can offer you, and I hope that makes sense. Okay, Prasad says, thank you, sir. Thank you very much. Appreciate it. NASA recently did the DART mission that will act as a full planetary defense system to protect us from potential asteroidal impact. What are your views on it? And do you think it will be effective, irrespective of the size of the asteroid? Yes. So, planetary defense from asteroid and comet impacts is something that's taken very seriously. We know what's happened multiple times in the past. Our good friends, the non-avian dinosaurs, no longer exist. They're no longer with us, very sadly. And they were wiped out by a massive impact, the Chicxulub impact event about 66 million years before today, which either fully or partially contributed to that catastrophe, that mass extinction. So it's something that is taken very seriously by organizations like NASA. So what is this DART mission? I think it's called deflection of asteroid something or the other. What is it? Okay, let's Google it, right? Why do we want to speculate? Let us Google up the exact full form of DART. Where are you, sir? Google. Here we are. What is DART mission? Not DART, simply DART. Double asteroid redirection test. That's what it stands for. So that is the DART mission. So it's I believe something that's going to happen in September. It's already been launched. When was it launched? It was launched some time ago. Okay, it was launched in 2021, and the impact is going to happen in September this year, September 2022. So what is this thing? This is a spacecraft that is designed to go and collide with a double asteroid system. Uh, so it's a double asteroid system, a large asteroid, which and a small asteroid that are gravitationally bound together. So it's like an asteroid that has a small moon of its own. And this DART spacecraft is going to go and impact one of these objects. I believe the moon, the smaller object. So the smaller part of the system, or maybe not, whatever it is, you can look it up. So let me explain the principle behind this. The exact specifics, you can Google it and see it for yourself, but let me explain the principles behind this. So let's say you have an asteroid, which is a high risk asteroid, which means it's an asteroid that in the future could collide with the Earth because its path in the future could coincide with the Earth at a later time, which means the Earth and this asteroid could be at the same time and place in the future. So that is a high risk asteroid. Let's say you have a high risk asteroid which has a significant probability of impact with the Earth, maybe in 50 years, maybe in 100 years, maybe in 200 years, maybe in 6 months, hopefully not. Yeah, let's say you have an asteroid like this. How do you ensure it doesn't collide with the Earth? You can use a gravity tractor. You could use you could use possibly nuclear weapons. You could use an impact. There are multiple ways of doing this. So this is a test of one of the ways of deflecting the asteroid. So what happens is this asteroid typically would have a mass of between 1 billion and 1 trillion kilograms. It's a massive thing. I believe its diameter is close to a kilometer. That's a massive object. This spacecraft would weigh about half a ton, 500, 600 kilos, something like that. It will travel at a certain velocity. It will go and impact this asteroid. The impact of the spacecraft into the asteroid will impart a certain amount of momentum to the asteroid. What is the formula for momentum? Very simple: mv squared. P equals mv squared, right? So it's the mass of the impactor multiplied by the square of the velocity. That's what it is. So the higher the velocity, the greater the momentum, and so on. So this impact will impart a certain amount of momentum to the asteroid, and it will change the velocity of the asteroid by, I believe, a couple of millimeters or 4 millimeters per second or something like that, whatever the exact amount is. It's a very small change in the velocity. Velocity is a vector quantity. Vector, it has direction. So it will change the velocity by a very small amount. You could call it a negligible amount. But if you take the effect of that and you take it forward by a few months, few years, few decades, then the trajectory of the asteroid will have a significant change, and you may be able to ensure that it does not collide with the Earth a few years or decades down the line. So that small little impact will eventually end up deflecting the trajectory of the asteroid and ensuring that it does not hit the Earth. So this mission, its objective is to test out this technology. We know it works, it will work, but we want to see exactly how it works. What is the effect of the impact? Because certain asteroids, we may believe they are very compact, but they are quite loose. Some asteroids are just piles of rubble. The consistency is like that of popcorn in a bowl. There was this reasonably recent experiment in which a spacecraft landed on an asteroid. I think it was asteroid Bennu, and they were shocked to discover this asteroid is a very loosely held together body, and its density is much lower than what they had expected. And the very slow touchdown of the spacecraft threw up a huge wall of debris, gravel and all that, from the asteroid. So if an asteroid is not solid, if it is just loosely bound rubble, then an impact like this could potentially just go through it and not have much of an effect or deflective effect on the asteroid. So it is important to test these things out. So that is the reason why the DART mission has been launched, and it's going to The impact is going to happen in September this year, and there's going to be a flyby of a CubeSat or something, which will actually give us visual images of the impact. So that's something very interesting. I look forward to it, and it will certainly be very exciting, and it will give us a lot of new information that we did not have until thus far. Interesting, very interesting. Okay, Karan says, apart from string theory, which theories are the other contenders for the theory of everything? For the theory of everything, which one do you think has the most promise? Well, the standard model of physics, which does not include dark matter or dark energy. So the standard model of physics is the best theory that we have thus far. It's been called the theory of almost everything, but obviously it's very deficient because it can explain only about 4 or 5% of the matter, of the mass energy composition of the universe, and that too there are certain loopholes in this theory, and yeah, so it's not a perfect theory. It is an approximate theory. It is the best jigsaw puzzle, the jigsaw assembly that we have made this far, but it will certainly be improved upon. So it has been called by some people as a theory of almost everything, the standard model. The other theory that is touted as the theory of everything is string theory. There are, I believe, 5 versions of superstring theory. Yeah, 5 major versions. So that is touted as a theory of as a potential theory of everything. Then there is M theory, the 11-dimensional M theory, which brings all of which is an outcome of string theory essentially. Yeah. So that is so M theory is a potential possible theory of everything. Then you have loop quantum gravity, which may be a very good, interesting theory. I have spoken about this in the past. I've gone into detail what LQG, loop quantum gravity, is. There's a small video clip on this channel. Look it up if you want more details. So loop quantum gravity is another candidate for a theory of everything. And then you have theories of gravity, of quantum gravity, because you would need to reconcile general relativity and quantum theory in order to have a theory of everything. So you have something like causal sets, which is an approach to quantum gravity that attempts to reconcile the two, and so on. So these are various candidates for being the theory of everything. I think loop quantum gravity shows promise. So if you were to ask me which is the the theory that has the most promise, maybe I would say loop quantum gravity. But obviously, it is not the final version of the theory. It's not a perfect theory. It needs to be worked on, but it's certainly very interesting. It says even time emerges out of quantum foam and quantum loops. So yeah, if you want to know more, check out my video on this channel, and in which I go into a little bit of detail about what LQG is. So that is the brief answer to this question. Okay, Ritvik Sardesai says, what is ethanol blending and how will it help us produce energy for transportation? So, what is ethanol blending? Let's first talk about what is ethanol. Ethanol is ethyl alcohol. What is the formula? C2H6O, I believe. Ethyl alcohol. You have methyl alcohol, then you have ethyl alcohol, and so on, then so on. So C2H6O is ethyl alcohol or ethanol, whatever you want to call it, right? What is it? It's just alcohol. It's the alcohol that humans can consume. It's the recreational drug that is the essential component of beer and whiskey and all of that. That's ethanol, right? Uh, so now this is a good source of fuel. In a typical fuel engine, in your car, in your scooter, vehicles, motorcycles, etc., we use petrol or diesel as the fuel that is combusted to produce energy, and that's what drives the vehicle. That's the mechanism, right? So you can also use ethyl alcohol in the same engines, in the same motors. You can. So instead of filling your tank up with petrol or gasoline or diesel or whatever it is, you could fill it up with alcohol, ethyl alcohol, and it will work just fine. So ethanol blending is when you mix about 10 or so percent, 10%, 20%, whatever the ratio is, of ethanol into your gasoline, into your petrol. So what you get is petrol with which has about 10 or 15 or 20 whatever percent of ethanol in it. It's a blended fuel, and that's what the government of India is trying to do in order to offset carbon emissions and all that. So how do you produce ethanol? You produce it by fermenting agricultural uh, agricultural essentially garbage, right? So typically, how do you make wine? How has wine been traditionally made? Let's say out of grapes. You crush the grapes, you let them ferment for a few days, and then you distill the thing. That's a whole process, and you get ethanol. You get the wine, grape wine out of it, and then you age it for whatever time. That's the process. So wine is produced, which wine is essentially ethanol. It is produced by fermentation of grapes, fermentation of hops, fermentation of potatoes if you want to make schnapps, and so on and so forth. You could also take leaves and compost, I mean leaves or cut grass or sugarcane stalks out of which all the sugar has been extracted. All of that you could ferment that and produce ethanol. So you are recycling agricultural waste products to create ethanol. That's great. That is a green technology. So then you produce ethanol using that process, and you use it, you blend it with your regular gasoline, with your regular petrol or whatever, and you offer that as fuel for vehicles. So that is the process of that is the principle behind ethanol blending. I believe the Indian government is working on this, and so that's what it is, and that's how it is. It's something that helps us produce energy for transportation, and it is something that is can be classified overall as a green technology, as a greenish technology. It's not entirely green, it has a carbon footprint, but it's better. I mean, if you are able to replace the requirement, the need for petrol with ethanol, then it's good for the planet, because you no longer have to extract crude oil, etc., out of the planet, and it's all good. So that is the principle, and that is what ethanol blending is. Okay, Gihan Jain says, can you please tell in short how antimatter is made? Antimatter. So first of all, what is antimatter? So antimatter is a weird form of matter. Antimatter particles, whether they are, so antimatter particles share the same mass as their regular matter counterparts, but the qualities such as electric charge and other charges, other quantum numbers, are opposite. So for instance, we have electrons in the regular world. The antimatter counterpart of the electron is the positron. It has the same mass as the electron, but it has a positive charge. The regular electron, has a negative charge. The positron has the same mass but a positive charge. Similarly, regular protons, have a positive charge. Antiprotons have the same mass as the proton, but they have a negative charge. The photon is the antiparticle of the photon, and so on, right? So that is what antimatter is. When you take protons, antiprotons, and positrons, you bring them together. If you make an anti if you make a positron go around an antiproton, you get antihydrogen. And similarly, you can create antimatter, anti-atoms, and so on. So that is what antimatter is. Now, how do we create it? Typically, antimatter is created in particle colliders, particle accelerators. You take two particles and you smash them together. This could be ions, this could be atoms, this could be protons, whatever. You take these. So let's say you have the Large Hadron Collider in CERN, Geneva. Yeah. So this is a particle collider. It's a particle smasher. You smash, I believe, protons together, or whatever it is. You smash them together at extremely high velocities, very, very, very high velocities, close to the speed of light. And the outcome of these collisions is new particles, because of this enormous amount of extra energy that's added to the particles, right? E equals mc squared. So the output of these massively energetic collisions is new particles. And typically, what we find is that when we create such matter in particle accelerators, we get an equal amount of matter and antimatter. So that is typically how antimatter is created. And one can, so you need a perfect or close to perfect vacuum, first of all, in these particle colliders. And then you would to store this antimatter which is created, you would need proper vacuum and magnetic confinement so that the antimatter particles don't collide with the walls of the container. The moment they collide, they come in contact with the walls of the container, they will annihilate and just give off pure energy. So that's how you create antimatter. But it's interesting, you should also know this, that our bodies, they emit antimatter. So a person who weighs about, let's say, 70 kilos would emit about 160, 170 positrons per hour. Positrons. Your physical body emits antimatter. If you weigh about 70 kilos, your body would emit about 160 to 180 positrons per hour. Where does this come from? It comes from the decay of potassium 40, which is a naturally occurring isotope that you ingest typically by eating bananas, but also from drinking water and eating food, and also from breathing. So there is a certain amount of potassium 40 that is available, present in food, in water, in the air, and there's a lot of it in bananas. Yeah. So if you have a truck full of bananas, that can set off Geiger counters. So your body emits antimatter, but a very small amount of antimatter. Isn't that fascinating? All right, next question. Saurav says, what is the possibility? Collapse of the Earth into the sun, or collapse of Earth into the black hole of our galaxy, as the galaxy has a spiral shape towards the center? All right, so what you're essentially asking is, what is the ultimate fate of the Earth? And as I hope you know, the ultimate fate of the Earth is intrinsically tied to the ultimate fate of our sun. The sun is our parent star, and everything revolves around the fate of the parent star. So the real question you are actually asking is, what is the ultimate fate of the sun and the solar system? And that includes the planets around it. So what's going to happen to our sun? The sun currently is your small average kind of yellowish star, yeah, in a very boring neighborhood of the galaxy. Yeah, it's going to remain this way. It was born about 4.5 or so billion years ago out of the remains of an older star. So the sun was essentially reincarnated from the debris, the debris of an older star. So in about 5 billion years from today, the sun will become a red giant. Because of the fusion reaction, because of the way the fusion reaction within the sun changes. So the sun is essentially a massive fusion reactor. What is fusing? It is fusing hydrogen into helium. Right now, that's what's happening. Eventually, what will happen is that all of the hydrogen in the sun will be used up in this fusion reaction. Hydrogen is being fused into helium. Once all the hydrogen is used up, the core of the sun will have to fuse helium into heavier elements like carbon, oxygen, etc. And the last stage is when carbon is fused into iron. And the thing is that when you have a fusion reaction of elements with mass numbers greater than 26, what is the mass number? It's the sum of the protons and the neutrons in the nucleus of that element. So when you have fusion of elements with a mass number greater than 26, then this fusion reaction uses more energy than is output from the reaction. That is essentially the death knell of a star, right? So in the case of the sun is a small star. It's not really massive. So what will happen with the sun is that in about 5 billion years, the hydrogen will be used up, and the sun the outer layers of the sun will expand and go outwards. It will become a red giant. Its diameter will increase massively. It will engulf the orbit of Mercury. Mercury will disappear and be burned. It will eat up Venus. It will also eat up the Earth. It will engulf the Earth. The Earth will then be within within the sun, inside the sun. So that process, that's going to happen at around 5 billion years from today. Then there will be this phase of fusion of helium into carbon, which is a very small phase, about 10 million or so years. Eventually, the outer layers of the sun will dissipate. The sun will no longer be powerful enough to hold them together, and the outer layers will just dissipate and go outwards. It will eventually become what's known as a planetary nebula or something like that. Then, at this stage, the core of the sun still exists, but it's no longer fusing. It's just really hot because of the history of the sun, and it's mostly made up of carbon. This is the white dwarf stage of the sun. So the sun will become a white dwarf, and it will remain a white dwarf for trillions of years and slowly, slowly cool down. At the end stage, all the heat, most of the heat will dissipate out into the atmosphere, into the environment, into outer space, into vacuum. And what will be left behind is what's called a black dwarf. What is a black dwarf? It's a giant diamond crystal. Giant diamond crystal, because the last stage is the fusion of what to what? Of helium into carbon. So at the end, you have this massive carbon nucleus, a massive ball of carbon, and it is extremely highly compressed because of the gravitational forces. So it's diamond. That is the allotrope of carbon that will be left behind. So it's a giant diamond crystal that you will have at the end of after trillions of years. So that is the ultimate fate of the sun. So what's going to happen? The Earth will be engulfed by the sun in about 5 billion years from today, and it will be burned out. All the atmosphere, everything will disappear. It will be just a hot, rocky object within the eventual nebula that will form from the death of the sun. Right? So that's how it's going to be. It will not be engulfed by it will not fall into the black hole of the galaxy because of the way gravity is. The black hole is not like a giant vacuum cleaner. It sucks everything inside. No. Even if you have a black hole that's going around the sun, it will not suck anything inside. It's just a massive object which follows the laws of physics. Right? And there could possibly be a primordial black hole in orbit around the sun. Possibly. Maybe that's what the so-called Planet 9 or Planet X is. This unknown thing that seems to be there, but we are not able to see it. Maybe it's a primordial black hole, a smallish black hole that is going around the sun, and that's why it's not visible. Maybe. Or maybe it's a planet that we still haven't found, because the solar system is vast. It's enormous. So that is the ultimate long-term fate of the Earth and the sun and the solar system. Right. Akash says, it seems like a great deal of time has passed since a big scientific breakthrough has happened, especially in physics. Is my observation correct? And if it is, how is it possible? Because we are far more advanced technologically compared to the 20th century because of engineering. Still, our perception of the universe hasn't changed much, scientifically speaking. Your observation is correct, Akash. The last great major breakthrough in physics was inflationary theory. Inflation. Cosmological inflation, which this theory was put forth, I believe, in 1980 or 1981 by Alan Guth. So that was the last major breakthrough in theoretical physics, which has been proven by observational evidence. We find observational evidence of this, and that's why it is an integral part of the Big Bang inflationary cosmological model, right? Lambda CDM and so on. So that's the last major breakthrough we have experienced in physics. Before that, every year, every decade, there were major breakthroughs. Right? In the 20th century, there were so many breakthroughs in physics. The entire world was transformed and revolutionized. You had relativity, special relativity, general relativity. Then you have quantum physics. You had the rudimentary quantum theory, the discovery of the quantum nature of the world. And then quantum theory took off. It took a few decades, but then you had quantum field theory, then you had particle physics, then you had the understanding of what particle physics really is, the symmetries of nature, the eightfold path, and so much more. Then you had electroweak theory, and all that remains now is to understand what gravitation is. So since 1981, there's been no new breakthrough, no new massive major discovery. We are still essentially where we were in 1981. The 21st century was hoped to be, expected to be the century in which we will finally figure out what gravitation is. We have not moved 1 millimeter forward since the 20th century in terms of our understanding of what gravitation is. And all of the progress that's happening is, like you rightly say, it's because of engineering. We are Our engineering prowess is what is taking us forward technologically. So we have more and more computing power, better computers. We have more miniaturized devices like smartphones and all that. Technology is progressing. It's engineering that is doing it. But there is no new fundamental breakthrough in physics. The big questions they still remain unanswered. So that is what the situation is right now. We have hit a brick wall and we are not going forward. Why is it so? Why is it so? Well, there are multiple reasons. We are not thinking differently. If we are facing this problem, we have to change our way of thinking. We have to change our approach to solving the problems. We can't just keep on doing the same thing over and over again and hope for something different. That's the definition of madness, I believe, isn't it? Doing the same thing over and over again and hoping for a different outcome each time doesn't work. So what's happening right now? Everybody, especially the West, especially the US, is deeply invested in string theory. String theory has taken over almost every single theoretical physics department. Most of the funding is being poured into research in string theory, and you see so many papers being published every week, every month, every year. So many papers you will find being published every single day. You can see them on the physics archive and in other places. There is so much output, research output, and yet it's taking us not 1 millimeter further ahead. So clearly something is wrong. There is this attitude of publish or perish in academia. So the entire focus is on publishing, output, volume, throughput, but it's not taking us forward. And the string theory mafia has choked all progress, essentially. That's what is happening. That's what's happened for the past many decades. I'm not trying to disparage string theory, but it has not produced any results. It has not produced any results. It's not taken us forward. It's produced wonderful papers and beautiful mathematics and very complicated mathematics and all that, but it's not taking us forward in physics. So definitely it's time to rethink our approaches. We need funding in other fields of physics, in other branches of physics, in other approaches, right? So that's where we are. The string theory mafia essentially has ensured that we are at this impasse right now. So yes, your observation is indeed correct, and we need a change of approach totally. Right now, it's all groupthink. Just do the same thing over and over again. Everybody must do string theory, otherwise you don't get funding, you don't get admission for your PhD and all that. That's how it is in the US. So that's why I say that the string theory mafia has taken over. There's a stranglehold. You want to do a PhD in theoretical physics, most likely you have to go into string theory. That's how it is. You want to take some other approach, you won't get funding, and you won't be accepted. That's how it is. So that needs to change. Maybe things can change in other countries. Maybe if we in India could get our act together and reform the education system, maybe we could throw up a few breakthroughs, but we are far from doing that right now. So that is the situation. Excuse me. Pushpendra Singh says, how does a wounded organism regenerate to exactly the same structure it had before? Well, it doesn't regenerate to precisely the same structure, but essentially the same structure. So let's say we know how it is, right? So why is it so? How does the body know that it has to regenerate exactly to the same in a certain way? How does it know? It is because of the information that's encoded in our genome, in the DNA. The DNA is a blueprint. The DNA is the blueprint to the entire organism as to how the proteins should code, what proteins should code, and what should happen. So that it's because of the information that is passed on from generation to generation, encoded in the genome, in the DNA of the organism. So when the organism is wounded, let's say it loses some part of the body, let's say it's a microscopic organism, or multicellular organism, lower life form, it knows how to regenerate, and the regeneration is done because of the information encoded in the DNA. Even some species of lizards like salamanders, etc., even if they lose a limb, they can regrow the limb, and the new limb that is regrown after a few months or weeks or whatever it is, time period is essentially the same as the limb that was lost. So it is because of the genetic blueprint provided in the genome, in the DNA. That is how the tissues, the organs know. I mean, the body, the physiology knows how uh, to regenerate the tissue, in what form it is to be regenerated. It is all because of DNA. DNA is the blueprint of the organism. Okay, two questions in one. Arnav says, was the first moon landing done by the US during the space race era, Cold War era, real or fake? Tejas says, why do many people still believe in the flat earth theory? And also, why do many people believe that NASA's first moon landing was fake? Okay, the first part of the question is, was the moon landing real or was it faked? Well, India's Chandrayaan mission has taken pictures of the surface of the moon, which show uh, that the Apollo lander is still present on the surface of the moon, right? It shows the tracks of the astronauts who walked around, and other artifacts from that moon landing. So clearly, unless the Chandrayaan spacecraft is also fake, unless it is, I mean, obviously it's not fake, right? So clearly, it really happened. The other thing, look at it this way: we know for certain that the American government invested 2 or 3% of the entire nation's GDP in the 1960s into NASA. We know that for a fact. A huge amount of money was poured into NASA. We know that. It employed so many scientists and engineers. We know that. Right? We also know that they built so many rockets. The Mercury program, the Gemini program, and eventually the Saturn program. We know that these rockets were built. We still have footage of the launches. Many of the initial tests failed. Many of them ended in explosions and disaster. Some of them actually went into Earth orbit. Eventually, you had a manned space flight program. We know it happened. There is enough evidence of the fact that these rocket launches, these human space flights happened. We have video footage, ample amount of video footage of all of these events, right? We also know that they built the Apollo rockets, the Saturn rockets. Saturn V, the most powerful rocket ever built until that time. We know that. We have seen the space launches. So we know all of these things happened. But if they have invested so much time, effort, and money and manpower into doing this, and they have rockets that actually work, then why is it so hard to imagine they actually worked and went to the moon? Then we also have photographic evidence of the moon landings, not just by the Americans, but by also by the Indians, by the Indian Chandrayaan mission. So if you take all of this evidence together, I mean, the only conclusion is that this actually happened, right? So yes, obviously, this is real. The moon landings were real; they were not faked. That is my understanding. If somebody has a better understanding, please feel free to educate me in the comments. I have an open mind. Right now, the other question is by Tejas: why do many people still believe in flat Earth theory and the moon landing was fake and all that? Look, consider this analogy. Consider this analogy from marketing and human psychology. People make a decision to buy something based on emotions. The purchase is made emotionally, and after you purchase the item, you justify it with logic. That is how the human mind works. So, most people don't have an understanding, a deep understanding of science. Most people, because of the education system, because it's so hard to study science, it's it's hard to invest so much time studying studying science, the scientific method, and so on. So most people rely on their understanding, rely on other people for their understanding of science. So they choose somebody, an influencer, a popular media figure, a writer, whatever. They choose somebody based on emotion, that yeah, this person feels good to me. When I listen to this person, he or she looks like he or she makes sense. Or maybe I like that person's voice, or maybe I like the person's face. That person appears to be trustworthy. So you first form an emotional connection with that person, and then you take, once you have that emotional connection, you essentially start believing everything that they say is true. Or it could be a book. You like the style of the book, or whatever. So most people, they don't understand science, and then but they want to know about it. So they rely on intermediaries, they rely on middlemen to give them information about science in an easy to digest manner. And many of these middlemen are not quite correct in the way they interpret science. Maybe they do it on purpose, maybe they do it because they sincerely believe it's true, whatever the interpretation is. That is why many people believe in flat earth theory and believe that the NASA moon landing was fake. And there are religious reasons for that too. Many religious figures, especially in the Abrahamic religions, uh, they still propound the flat earth theory, that all of this is wrong and all that. And people who are religiously inclined, who derive emotional comfort, etc., from religion, they will be very much predisposed to believing everything wholesale. So these are a number of factors why people believe such things: flat earth theory, fake moon landings, all of that. Most people don't have um, the intellectual background, the scientific training required to discern what's right from what's wrong, and what data is telling you, as opposed to what data doesn't tell you. So these are the reasons why you have these attitudes and these beliefs that still persist as of today. But the thing is, in India, there are very few people who believe in the flat earth theory. It's in the West, in the US, etc., that lots of people believe in flat earth theory. Now ask yourselves, why is it so? That is homework. Go ahead. And what do you think? Let me know in the comments. Not in the chat, in the comments, once this stream is done. All right, next. Swapnil says, since Pluto crosses Neptune's orbit, astronomers have long wondered, why don't the two celestial bodies collide? Some simulations predict that Pluto should have collided with Neptune or escaped the solar system. So what's keeping Pluto stable in its technically chaotic orbit? Gravitational mechanics, celestial mechanics, right? The data that we have is data from the past couple of centuries, past 50 years, past 100 years. The Indian astronomical data that was transmitted to the West may have spanned a period of 5,000 or maybe a few more thousand years. That's an eye blink of time in the cosmological scale, in the scale of the lifespan of the solar system. So the truth is that many of the orbits that we have in the solar system today could be unstable orbits. It is almost a certainty that the orbits have changed, that many ancient protoplanets that were once in orbit around the sun would have been ejected out of the solar system. Many of them would have collided. The asteroid belt is testimony to an ancient collision in which two or more protoplanets or ancient planets collided and got destroyed. The fact that Saturn has rings is testament to such a violent event. It's possible that Earth was struck by an ancient planet, and that gave birth to the moon, and so on. It's also known that the orbit of Jupiter has changed over time. That's what the best simulations tell us, and that's why it's able to shield the inner planets from massive collisions with asteroids. And we know that the orbit of the axis of rotation of Uranus, I believe, or Neptune, I think it's Uranus, is tilted at 98 degrees, which is again the consequence of an ancient collision with some other object. We know that the moon Triton is something that's been captured because of an unstable orbit. And it is also known that Pluto crosses the orbit of Uranus, Neptune, one of these, most likely Neptune. So that also is in a tilted and strange orbit. Pluto takes about 247 years to complete one orbit around the sun. For Earth, it is 365 days. For Pluto, it is 247 Earth years. So the solar system is still a dynamic place. The orbits are still evolving. In a few million years, it is possible that the orbits may have changed again. It's possible that Venus may be ejected out of the solar system in a few million years. We only have a very small snapshot of time for which we have data and information. These processes happen over millions and billions of years. So, in the future, Pluto may very well collide with Neptune. It may very well escape the solar system. Even Venus possibly may escape the solar system or may even collide with the Earth. These things are very, very possible, but over a very long period of time. It won't all happen in our lifetimes. Our lifetimes are an eye blink of time. What is 100 years? It's nothing in the cosmological scale. So, so that's the answer. These things, this is all still happening. In a few million orbits in the future, Pluto may end up somewhere else. It may end up colliding with Neptune. It may end up escaping the solar system, and all of these things, all of these options are still very much open. Yeah. So what we are seeing is a moment frozen in time. Our lifespans are so small that what we are seeing is just a few moments in time. That's it. But the whole story is much, much, much longer than that. Right? It's like you're watching a movie for 3 seconds and you're asking, why did nothing happen? You get it? So that's how it is. Okay, Reyes says, how can a human life be extended, and can it be done in this century? Please shed some light on this. This is the age-old quest of immortality or longer life. How can we live longer? Can we live longer? Can we live 100 years? Can we live 150 years, 200 years? Wouldn't that be great? So can human life be extended? So to answer this question, we have to ask ourselves, why do humans die? It's because of the process of aging. Eventually, aging deteriorates the body to a certain extent that it cannot sustain life, right? So that is death by natural causes. So how do you slow aging? If you slow aging, then certainly you can extend human life, right? So let's say aging happens at a certain rate, dx by dt. Let's say you make that rate half. So 1/2 of what it was, then you may be able to double your lifespan or something like that. So what causes aging? It is believed that one of the primary contributors to the process of aging is the shortening of the telomeres in human chromosomes. So human chromosomes are what make up our DNA in the nuclei of cells, not red blood cells, but other cells. And at the ends of chromosomes, you have these structures called telomeres. These telomeres, when you're born, have a certain length. And as you grow older, the telomeres, their length gets progressively shortens. And it is believed that it is this shortening of the telomeres that causes the process of aging. And therefore, one of the keys to slowing down aging or maybe even reversing it could be ensuring that this process of the shortening of the telomeres doesn't happen, or maybe figuring a way out to reverse it or stop it. So there is a lot of research being done about this. I believe there are, I don't remember the names, but there are some scientists, some very prominent scientists, biologists, etc., who are working on this. So that is the primary approach that I know of as of today that people are taking towards the science of possibly how to reverse or slow down aging, and that would obviously have the consequence of extending human lifespans. So it could happen this century, conceivably. That is the best answer I can offer you. Do your own research. It's an interesting field, and that also has other questions that pop up from that. I mean, Is the human brain capable of functioning well beyond a certain age? You may have a body that stops aging. Will it also stop the deterioration of the human brain, of the human mind, dementia, senescence, or whatever you call it, right? Mm. So, yeah, these questions are still unanswered, but work is being done on this. Okay, Karan says, where is Voyager now? Does it still send any data? So Voyager is not one thing, it's not one spacecraft. There are two spacecraft, Voyager 1 and Voyager 2. Strangely enough, Voyager, okay, I think Voyager 2 was launched before Voyager 1, a month or so apart. So both of these spacecraft were launched in 1977. And the objective, the purpose of these two spacecraft was to photograph the gas giant planets of our solar system: Saturn, Jupiter, Uranus, Neptune, essentially, and their moons, if possible. So these were great successes. Both of these spacecraft did a great job of photographing, giving us the first good photographs of these gas giant planets. Beautiful photographs that people still put as their wallpapers and all that. Yeah. So that was the original objective of the Voyager spacecraft. So as of today, I believe Voyager 1 is roughly 150 or so astronomical units away from the sun, from the Earth. What is an astronomical unit? It is the distance between the sun and the Earth. That mean distance is called 1 astronomical unit. So as of today, 2022, Voyager 1 is about 150, between 150 and 160 astronomical units away from where we are. That is about 23 billion kilometers from here. So that is where Voyager is as of today. It is now technically in interstellar space. It has technically left the solar system. It's now in interstellar space. It is still sending back data, and that data has helped us understand a lot about what the environment of interstellar space is like. What is the termination shock like of the solar system? What is that? So all of these various regions of space, we have been able to understand them better because of the data that Voyager 1 and 2 have sent back to us. It is still sending us data, but the power supply on this spacecraft, on Voyager 1, is now failing. It will probably fail by 2025, which means that this spacecraft will most likely stop sending us data, stop collecting and sending us scientific data by around 2025, which means that we will no longer be in contact with it from that point onwards. From that point onwards, it's a dead spacecraft, more or less. It will go off into interstellar space for tens of thousands of years, millions of years, and maybe someday somebody out there may find it and figure out where it came from. So that's what it is. It contains this gold disk with information about where the Earth is, and there are recordings of voices from our planet and all that. So there is a certain amount of data on it, in the hope that somebody out there may find it someday. So that's where Voyager is. That is a status, and yeah, that's your answer. Your favor says, in the future, can technology remove the uses of ink, pen, and pencils? Yes, certainly. Technology can do anything. Technology could do away with the requirement for using pens and pencils. Today we have these touch screens. You could actually write stuff with your finger on it, or you could use a stylus like the Apple stylus or Apple pen, whatever they call it. There are such devices available for Android as well, and so on, right? So yeah, you may no longer need ink, pens, and pencils. You may no longer need paper, and so on. So technology can certainly do it, but is it something that will gain wide acceptance? Will everybody have the money to shell out? The large amount of money that you need to shell out to acquire such a device? Is it going to be practical? Is it something that will be able to be adopted widely by everybody all across the world? These are questions that still remain. Sometimes technology takes things too far, which you don't really need. Let me tell you an interesting story. So in the 1960s, the Americans and this 1950s, 1960s, and 1970s, the Americans and the Soviets had this massive space race, right? They were both vying to be the number one spacefaring nation on the world because of various considerations, including military technology. Space has a military dimension, so on. So the Americans and the Russians were competing for supremacy in the space race. And the Americans had astronauts, the Soviets had cosmonauts. Yuri Gagarin was the first cosmonaut. Valentina Tereshkova was the first woman in space. Neil Armstrong was the first human being on the moon, and so on. Right? So they had this space race. Many years later, when things were better, when the Cold War was more or less over, one of the American astronauts met a Russian astronaut, and they had a conversation. They exchanged notes and experiences and all that. And the American guy, I think it was Neil Armstrong, if I'm not mistaken, he asked the Russian guy about how did you write in space. The American guy said that we in NASA, we had this massive research program as to how to create a pen, how to build a pen that works in space. The ink should flow the way it flows on Earth, and you should be able to write in space. So it cost the entire technology the demonstration and creation it cost millions of dollars, and eventually they were able to create a pen that worked flawlessly in space. Yeah. So the American astronaut asked the Russian guy, how did you guys write in space? The Russian guy said, we used a pencil. No need to invest millions of dollars developing a pen with ink that works in space. They just used pencils. They solved this problem with a low tech solution. So yeah, that's an anecdote, but you don't need to remove everything and invest in expensive technology to replace things that don't really need replacing. Of course, paper is a problem. The more humans we have, the more paper is required, and the more trees you need to cut. That is definitely a problem, but which would need a solution. But overall, to use technology to get rid of pens and pencils seems, as of today, a little bit of overkill. Okay, Alpha says, can you briefly tell about Saturn's hexagon? So why should I tell something when I can show you a picture? A picture is worth 1,000 words. Okay, Saturn. Let's go to Saturn hexagon. So there you are. It's something that's on the polar regions of Saturn. This massive hexagonal arrangement of the clouds of the top layers of the Saturnian atmosphere. This is the shape. It's a reasonably hexagonal shape, as you can see. There are vertexes at the center, and there are other storms as well within the hexagon. This is another image of that, and you can see various representations of the hexagon. And this red image here is the central vertex within the hexagon, right? This is another image of that in different colors. So this is the hexagon, Saturn's hexagon. Now what is it? It is a certain shape, a hexagonal shape that has emerged out of the complex fluid mechanics and dynamics of the Saturnian atmosphere. It's something that seems to exist on the top layers of the atmosphere because of the complex interplay of the various gases, kinds of gases that are there in the atmosphere. They would exist at different temperatures, and they would mix in certain ways. So this is a consequence of the fluid mechanics of the Saturnian atmosphere. Fluid mechanics is an extraordinarily complex field. The equations that govern fluid mechanics they look deceptively simple, but they are incredibly difficult to solve. Typically you need supercomputer simulations and all that. So I don't have the exact answer as to why you have a hexagonal shape there, but it is because of the interplay of the various fluids and gases in the atmosphere, which has thrown up this sort of shape. And I believe various scientists in certain universities have tried to replicate this sort of phenomenon, and some of them may have succeeded. So it's a consequence of the complex fluid mechanics in the atmosphere of Saturn, which involves the various gases of the atmosphere, various compositions, various mixtures, various temperatures, various densities, and all that. You take all of these various different parameters together in a planet of a certain size, and it throws up this sort of geometrical shape. When it comes to other planets, you have different shapes. You don't have any hexagon on the Earth's atmosphere. You don't ever see that at the poles, right? But for instance, when you take a body like Titan, Titan is a moon of Saturn. It has a very thick atmosphere. On Titan, at the poles, you have these vertices. The Titan's atmosphere is very thick. It's composed of hydrocarbons. It's a very cold atmosphere, but very thick. And at the poles of Titan, you have these vertices, which are like roughly, uh, what's the shape called? Spiral kind of shapes. Yeah. So it's a smaller, much smaller object, and you have spirals there. But on a gas giant like Saturn, you have a hexagon, which you don't see on Jupiter again. So it's a very complex phenomenon to which we have no ready answer. But the basis of this phenomenon is fluid mechanics. Okay, Abhijit Verma says atoms never touch each other, for if they ever did, there would be a huge explosion. Then what creates a sensation of touch? What creates cause and effect when a billiards ball hits another one, when Rafael Nadal hits a forehand? Okay, so if two atoms were to collide, you would not really have an explosion. What happens is governed by nuclear physics, and within that there is quantum mechanics and so on. So that's a different topic. So what causes the sensation of touch? What is behind the cause and effect sequence of a billiards ball bouncing off another one and all that? The real question you're asking is, why does matter occupy space? Why does matter occupy space? Why is it solid? Why is it reactive? And so on. And the principle at the heart of this is what's called the Pauli exclusion principle. So what is the Pauli exclusion principle? It's something that is part of quantum mechanics, quantum physics. The Pauli exclusion principle says that two or more identical particles with half integer spins, that is fermions, cannot occupy the same quantum state within a single quantum system simultaneously at the same time. Okay, it's about fermions, particles with half integer spin. What are fermions? Fermions include all the quarks, all the leptons, all composite particles made up of these, made up of an odd number of these, such as baryons, atoms, nuclei, and so on. These are fermions. And because they cannot occupy the same quantum state simultaneously within a single quantum system, that's why matter takes up space. That's why matter occupies space. That's why you cannot squeeze matter beyond a certain limit, unless you want to create a singularity. I mean, that's possible beyond a certain that is general relativity. That's a whole different thing. But that is the reason why matter occupies space. That is why matter is hard or soft or whatever, depending on the properties. It is all because of the Pauli exclusion principle, right? Atoms can touch each other, they can merge together in the process called fusion. That's a whole different story. But the reason why matter occupies space, and the reason why you have the sensation of touch and the sensation of the cause and effect thing of billiards balls bouncing and all that, it is all because of at the heart of all of these phenomena is the Pauli exclusion principle of quantum mechanics. So you can explore that further. That's what I can tell you in brief. Alpha says, when humans discovered nuclear fission and fusion, they created weapons rather than using that energy to power machines. Is this the greatest stupidity of mankind? When humans discovered fire, they used it for cooking. They also used it for warfare. When humans discovered metals, copper smelting, iron smelting, they used it for building utensils, for building various things, and also for building swords and knives and weapons. All technology has multiple uses. When humans discovered nuclear fission, they built nuclear reactors that can be used to produce energy, electricity, etc. But they can also be used to develop nuclear weapons. So that's just how it is. Technology is purpose agnostic. Technology just exists, but how you use it is up to you. uh, Ideally you would want to use all technology for good purposes, non-destructive, non-military purposes, but that's not how the world works. So is it stupidity? Well, if that is the greatest stupidity of mankind, then humankind is stupid by nature inherently, and so are our closest relatives, the chimpanzees, who are also just as inherently violent and stupid as we are. So technology is purpose agnostic. You can use it for whatever purpose you want. A stick can be used for playing drums, it can be used for cracking skulls. I mean, that's up to you, right? So yeah, I mean, there's no value judgment in this. That's just the way we are as a species, and all technology can be used for a variety of purposes, including destructive purposes. That's just the way it is. Secret Santa says, I would like to know what is your opinion on the Feynman Lectures books. Is it a good book to understand physics for beginners, or the fundamentals of physics recommended by you is a better option? Uh, the Feynman Lectures are obviously a series of books written by the great Richard Feynman, the great physicist Richard Feynman, who was a Nobel laureate. These books, they are well, they are. People say that these are books for beginners, but that's not the case. These books should be used by elite level students, the top 1% of the students. It is not something that is suitable for beginners, even though they may be uh, portrayed as beginner level books. The Fundamentals of Physics by Halliday and Resnick, or whatever else is the standard text that is used in schools and colleges, etc., that is the right place to start if you want to learn physics from scratch. The Fundamentals of Physics by the Feynman Lectures is something that should be studied by elite level students, the top 1%. That's only when you have mastered the fundamentals can you go into the Feynman Lectures, and then you will understand the fundamentals even better from a different perspective, from the perspective of a genius physicist. So when I was a kid, I tried studying the Feynman Lectures as a beginner text. Did not work for me. I had to go down to the level of Halliday and Resnick, study that thoroughly, master that, internalize that thoroughly by solving lots of problems. Then later on, when I reopened the Feynman Lectures, they made a lot more sense to me, right? So it is not for beginners. It is not even for ordinary students. It's for elite level students. That is my perspective on this. Tejas says, until the 10th standard, I was a science enthusiast, but due to my JEE preparation, I hate science now. What should I do to restore my love towards science? That's an interesting question. Let me give you a strange example. Let's say your favorite food is pizza. Pizza, yeah? Let's say your favorite food is pizza. You love it more than anything else. Now, what if I were to force you to eat nothing but pizza, not twice or thrice a day, but 6 times a day for an entire year? Let's say one of these days you feel like eating masala dosa with sambar. I say, no. You want that taste? You need to have that on a pizza. Masala dosa sambar flavor on pizza. Let's say one day you feel like having aloo gobi. I say, no. You want that? You need to have that on pizza. Aloo gobi flavor on pizza with the aloo gobi toppings. Let's say you want palak paneer. I say you must have it on pizza. Palak paneer topping on pizza. So I force you to eat pizza 6 times a day, and nothing but pizza 6 times a day for 365 days continuously. After a year, will you still love pizza? Will you still think it's your favorite food? No, you will be sick and tired of it, right? So that is the kind of thing that happens when you force somebody to do something that they love, even they may love it, but you force them to do it over and over and over again for a long period of time. They will get tired of it, no matter what it is. So maybe you love science. And why does somebody love science? Because you're fascinated with science, you find it fascinating, and you want to learn it, and you want to go to the next level and the next level and the next level. You want more and more knowledge because it's so interesting. But when you're preparing for an exam, you're not learning anything new. You are staying at the same level, but you are practicing over and over again, problem after problem after problem. And all you are trying to learn is how to get good marks in an exam. It's no longer about loving the subject, it's just about passing an exam. That kind of kills the joy of learning the subject. Now, don't get me wrong, I'm not saying you should not study for exams. It is a necessary part of life. Unfortunately, the way the education system is today, you have to get to pass exams, and you have to get good marks and get a certain ranking or whatever, because that's how you get a degree or admission, and that's how you get a job eventually. That's just the way the world is. Certain things you have to do, but yes, it can kind of kill all the joy of the subject, of the joy and the fascination that you had for the subject. So let's say I forced you to eat pizza for 6 times a day for a year. How will you rediscover your love for pizza? By taking a break for it for a while. So let's say you have done your JEE, you got a good ranking, you got admission to your IIT or whatever. Then take a break for a while before you have to go and join the IIT. Just detoxify your mind of that. Do something else. So that would typically be how you do it. But if you had a love for science inherently, then I think you can certainly restore it after a while. You just need to ensure that the burnout stage is behind you in the rear view mirror. So that's what I would offer to you. There is no hard and fast rule of how to rediscover your love or restore your love. Typically, you take a break from something for some time, and then you can recharge your mind and maybe hopefully rediscover your love for the subject. So typically it's like this. uh, when you are doing research, you're always learning something new. You're trying to discover something that nobody has discovered thus far, which means you're going deeper and deeper into the subject. But that is the joy of discovery. You may have to work 8-12 hours a day every day for 5 years, 10 years in the pursuit of what you're trying to discover. Albert Einstein went essentially, he disappeared from 1905 to 1915 in the quest of the general theory of relativity. It took him a decade of relentless hard work. He did not lose his love for physics, because he was doing it from the purpose of discovery, right? He was every day he was making some progress, he was discovering something new. As long as that is there, you will not feel that your quest is pointless. But when you're just forced to study for an entire year for an exam and you're not learning anything new, you're just practicing, that can kind of burn your mind out, especially when you have to do it like 8 or 10 or 12 hours a day, the way some people have to do. So yeah, when you are in that situation, the best remedy is to take a break as long as you possibly can. So that could possibly do the trick for you. Shubham says, I will be in a graduate program for mathematics from fall 2022. How should I choose one area of research in mathematics? As of now, I like algebra, like Lie algebra and representation theory, functional analysis and algebraic number theory. However, I have not been able to decide one area for research. I have funding available for 6 years, and I am sure I won't be able to research on all these topics within this time period. Could you please advise me something so that I can get out of this dilemma? Okay, so I will give you a general rule of thumb as to how to do research when you're starting off. You are going to go into graduate research, graduate program, which is the master's level, and eventually it will culminate in a PhD, right? And you have funding for 6 years. So typically, you would do a certain piece of research for your master's level requirements, and there'll be coursework in that. And then for your PhD, you will do possibly a different kind of research. The rule of thumb is that when you are starting off, when you are in graduate school, don't try to bite off more than you can chew, which means don't try to tackle a problem or take on a problem that will give you a Nobel Prize or a Fields Medal. Don't do that. Don't take something that's massive and very difficult. Take something that will produce original, genuinely original research, but it's not too hard and too complicated. You just need to get your degree first. You need to reach that milestone. Once you get the degree, and then when you go further in your career, you can take up the bigger problems. So don't take on too many things, and don't try to tackle enormous problems. Keep it simple. Make sure that the problem that you take will advance the field in some way, will ensure that you have done original research, but don't make it too difficult and too complicated. So that is the simple rule of thumb that I would offer you from a lot of experience, and yeah, from my experience, right? So that's the best advice I can offer you. Simple advice. All the best, sir. Ashish says, is it easier to understand other subjects if one understands the hard sciences? Uh, Typically, a person who understands mathematics and logic can understand anything, anything. And the basis, the foundation of all the hard sciences, physics, chemistry, biology, etc., is mathematics and logic, and the scientific method, which is logic, right? So yeah, who is it? Ravikant, right? The great, the famous investor. He says that if you understand math and logic, you can understand and master almost anything. And I totally agree with that. That's been my experience also. And I realized this quite late, that yeah, I can understand lots of different fields because I have the advantage of knowing math and physics and the scientific method, which is logic. So the short answer to your question is yes, it is indeed easier to understand other subjects if one has a rigorous training and understanding in the hard sciences. Yes, it is indeed true. Alok says, is it okay to breathe? I highly recommend breathing. Yes, I highly recommend it. Okay, with that, we are at the end of today's questions that I have selected. Now, let us take some questions from the chat. If you have questions, do ask me in the live chat right now. Okay, Shahil says, if I don't get into IIT, should I use MIT OpenCourseWare computer science and engineering courses? Or are there any better options? See, why do you get into the IIT, or why do you try that? To get a degree, right? You can certainly learn the subject from MIT OpenCourseWare, but you will not get a degree at the end of the learning experience. So if you just want the knowledge, if you just want to master the subject, then I would certainly recommend the OpenCourseWare series, whether it's MIT, whether it's Stanford, or whatever else. It's all available for free on YouTube. Great resource. Even if you're in the IIT and if you want to understand the subject from a different perspective, or whatever, you could certainly take that as something extra to study. But if you want a degree, then you have to get into an institution, IIT or something else. So that's the options that you have. All right. How to be a polymath like Da Vinci? First of all, you need to be born extremely intelligent, genius level intelligence. Very few people have that. So if you have that, then you should explore your curiosity and study everything you can, read as much as you want, as you can. Essentially dedicate and invest your entire time into learning. That's how you become a polymath like Leonardo da Vinci. He was an engineer, he was a painter, he was an artist, he was a scientist. He contributed significantly to the field of anatomy. So he had so many different interests. That is the definition of a polymath: somebody who is more than competent, who is an expert in multiple fields or subjects: music, art, science, mathematics, and so on. So very few people can be that. You have to be at a very high level of intelligence and competence, genius level. So that's the first requirement. And then you have to be curious, and you have to invest the time and the effort in learning all of and mastering all of these different disparate disciplines. That's how you do it, sir. All the best. Right. What other questions? When will I show my bookshelf? Well, you can see some more of it now. maybe in the future I will take some photographs and just put it up on the community section, and you can take a good deep look at it. All right. Okay. Dungar Singh Chauhan, are space hurricanes dangerous? I'm not quite sure what a space hurricane is. I think it's some kind of interaction between the solar wind with the magnetosphere of the Earth, similar to the process that causes aurora borealis, aurora aurealis, australis, something like that. I think that's what a space hurricane is. Is it dangerous? A space hurricane is a symptom of a larger cause. I mean, if that's what it is. So what would really be dangerous is solar wind or solar storm, essentially, because that could interact with the magnetosphere, the magnetic environment of the Earth, and it could potentially disrupt electrical grids and other systems on the Earth. That could cause a lot of problems. So that is what I can offer you right now. I'm not quite sure what space hurricanes are, which phenomenon is now called space hurricanes. But how about I look into it and maybe I can give you a more in-depth answer next time. So yeah. Okay, any other questions that would evoke my curiosity? What are white holes? White holes, I have answered this question, I think, 1 or 2 episodes before. White holes are essentially, you can think of a white hole as a time reversed black hole. So if you had a black hole, in a black hole, everything goes inward, inside, and there is an event horizon, which is a point of no return. Once any object, any particle, any human being or whatever crosses the event horizon, there is no way of them to re-emerge from there. It's the point of no return. If you were to reverse that process, then a white hole is like a time reversed black hole. It has an event horizon, and it is the point of no entry. Beyond that, you simply cannot enter. So in a black hole, you will see things going inside, objects falling inside. In a white hole, the gravitational effects are the same. But a white hole is the opposite of a black hole. Things emerge out of it. So essentially, a white hole is like a time reversed black hole. Right? Constant Change says exams kill curiosity subjects. What to do, sir? Well, there is no remedy to it right now. The education system is such that everything depends on exams. Exams are high stakes things, and you have to get good marks in exams in order to achieve whatever great objectives you have. I know they kill curiosity. They kill the joy of life. They kill the joy of the subject. That's what it is. That's not how the system should be. A better system would be continuous evaluation of a student's performance throughout the year, not through exams, but by other means. There are lots of other examples in other countries that you could take a look at. But as of now, this is what we have. Exams have to be dealt with. So all I can say is deal with it, and once you are done with your exam, take a break, and hopefully that will recharge your mind, and then your curiosity will be hopefully brought back to where it was. That's all I can offer right now. Okay, do we have any other interesting questions? How is emotional intelligence necessary in life? I like to define things. What is the definition of emotional intelligence? I don't have a definition for that. So the answer is I don't know. I don't know what it is, first of all. I know what intelligence is. It is the ability to learn things rapidly and apply the learnings in solving problems and dealing with life and situations and problems. That is the rough definition of what intelligence is. Now, what is emotional intelligence? I don't quite know. I know people have written books about that. I may even have a book somewhere lying around about emotional intelligence. I've never read it. Never made sense to me. I may have started reading it, but I couldn't wrap my mind around it. So yeah, I don't quite know what it is. What I can say is what is necessary in life is emotional stability. Most people are governed by their emotions. Sometimes they're happy and things are great, they can do things. Sometimes they're upset and they cannot do anything. The plans change depending on the emotions. The agenda of the day changes depending on how what your emotional state is. So many people, if not most people, are greatly driven and governed by their emotions. Their emotions govern their life. That is bad. That is bad. If you are a person who is driven and governed by emotions, you will not achieve much in life. You need emotional stability. Even when you're feeling bad or good or whatever, the best thing is a plateau of emotions where you are, equanimous. So that comes through, I don't know. Some people are born with it, some people need training, some people need meditation, some people need other things. But what I would say is most important in life is emotional stability. Don't allow your emotions to drive you and govern you. Right. Okay, any other questions? Any other questions? One lecture on pyramids of Egypt. How is it built? Um, yeah, it's architecture, it's technology from that time, a few thousand years ago. So yeah, I'm not quite sure how they built it. Maybe it's a mystery. So yeah, maybe I will look into it. Maybe, yeah, maybe. Okay. There are lots of questions about history and geopolitics. Today is the day of science, my dear friends. Um. Okay, I guess we are. I guess that's it for today. There are lots of questions, but I'll call it quits at this point. Nearly 2 hours. So thank you. Okay, let's take one one last question, which is it a scientific question? Sagnik says, is it okay to not get Married. Well, science has no opinion about this, so it's your choice. It's your choice whether you want to get married or not. It's your choice. Who am I to tell you whether it's okay or not? It's for each person to decide for themselves. There is no right or wrong in this. So I would say that if that is what works for you, if that is what makes you happy, then go ahead with that. Go ahead with that. You should go ahead with whatever is best for you from your perspective. All right. And with that, I will end today's session. Thank you very much. Great talking to you all. And I will see you in tomorrow's history, geopolitics, and current affairs session. Until then, take care and see you. Bye.